I don't have here any specific agenda, so I just speak what comes into my mind, and I try to show what I think is relevant in the beginning. So that would be the procedure. So I can first show just quickly how to install it, and well, just to walk through what is the phases, and then I can show something on the models and how to run the simulations and configure the inverter and set up the simulations and talk about that side a little bit. But that would work as an introduction. Then whoever starts using this, would that be okay?
Yes.
Yeah.
Yes, fine.
Yeah. So I have now opened this Matlab. I'm using here the version 2020A. But basically, we have two options here. So this first installation package that was generated in the beginning, it was based on this Matlab version 2018B, and there are some Matlab and Simscape version dependencies, and this version is now working only with the 18B version. But this other installation package, so this one is compatible with 19A and newer versions. So I am now showing this using the 20A version, and therefore as a demonstration I install this one. So it starts like just by double clicking the installation package, and I close this one, and now it can be seen here as an additional toolbox in the add-on manager. So basically, if you wanted to get back into this window, you can go to the add-ons and select manage add-ons, and I'm back here again. So basically, this is the location where it is seen when it is installed, and it can also be uninstalled from the same view here. And now the add-on has been installed, and the next phase would be to install the license, and it can be done semi-automatically by opening the Simulink, and I just show that when I create a blank model here, just a second, it is opening. So it is first loading the Simulink, and once it is ready, it shows this blank project file. But basically, now that the add-on has been installed, it can be found from the Simulink toolbox browser. So all the components and what is included, it can be browsed using this library browser tool. So this is now an untitled new model, and I go to the browser using this icon here, and now I can see this one, the Drive SmartGrid here, as a new toolbox library. And basically what is included here, there are two demonstrations models. One is the inverter operating in the AFE mode, and in the second one it is operating in the microgrid mode. So both are the grid converter model, but the operating mode is different in these example models. And here you can find this is basically the inverter model that is used in the models. So I will show that one in more details. So let's open this one here. I double click on the icon here, and once I try to open that one, the toolbox notices that I don't have the license key yet installed. So it automatically opens this file browser window here, and now I'm navigating into this folder where I have stored this license key file that I sent you last week. So I choose it and open it. So now it automatically installs the license key into a proper location. So this is basically the installation folder of the add-on on my computer. And once it is started, it shows this startup banner. So this is an indication that the key was installed successfully and you are ready to go. And now we can see that I have still this untitled blank project file open here in the background. So I just use this to access this library browser icon here. But now I'll just save it so that I don't overwrite the original file. So I put it here. Just make a copy of that one. So this is now an example model where we have the grid converter here. It is supplied from a battery, and in this case, this is now configured as a relatively simple battery model. So this is more like a constant voltage source, but this can be configured also so that there are the battery dynamics or other charge behavior is included in the model. But for these simulations that I show here, it is the capacity is so large in the battery that it is more like a fixed voltage source. And if we look on the left-hand side, this is here now the AC network. So the AC voltage source here. So it is the three-phase network, and now this is just this how it looks in the model. So the three phases are now bundled here and shown as only a single wire, but the three phases are here. And this is where the line current is measured, and it is taken into this block here. So this is basically a scope window where you can monitor the signals, and basically you can take many signals into one scope block and view them in the same window. I will show it later, but that's the principle. And the idea here is now that this is the AC network here, and this was the battery on the right-hand side, and there is one load here which is operated using this breaker here. So what is done during the simulation is that this we saw that how we can transfer the load from the supply network to this battery storage here. What is more in here, there's the transformer which can be configured so that these are Simscape original models. So basically, I can show it a little bit later, but there's a library of different power system and power electronics components that you can use to build your own simulation. But in this case, this is now taken from the Simscape library. So if you look at the overview of this model, so the component that is provided in the Danfoss library, it is basically this inverter component here, and everything else. The idea is that you can build this using the original Simscape and Sim Power Systems components. So it is like you can use this inverter model, which is a copy of the NXP Grid Converter, and you can use it together with the other toolboxes to build larger system models and investigate their behavior. Next, so let's zoom in a little bit. So I open this by double-clicking the icon, and it looks like this. So on the page that opens here, we can see these 3 different subsheets. And on the first one, there are the hardware settings. And here you can choose what is your inverter rating. So the available inverter types are listed here. And we can see the different current ratings and the voltage classes also. The filter type can be also configured. So there's the list of available filter models. This relates this EMC configuration to the HF capacitors, which are in the VACON LCL filters. But in these simulations, mainly this is not a relevant thing. So, but anyway, this can be configured so that those capacitors are either connected to the protective earth or not connected. So it is left, let's say, like for some special considerations. And it is also possible to initialize the DC bus voltage here. So in the beginning of simulation, you can start from this DC bus voltage, so that you don't need to build all the charging circuits, etc. But you can just take some shortcuts and go directly into the simulation phase by having this possibility to parameterize the initial voltage. And here on the second subsheet or a sub page, these are the inverter software parameters. And this now, the grouping of the parameters, it is similar to what is found from the actual grid converter if you connect using the NC drive and open the inverter parameters or the application parameters. So the grouping is similar. So for example, if we look at some of these groups, so in the first you can set the nominal ratings, the voltage and the system current, and so on, and you can access the reference parameters like DC bus voltage reference or reactive current reference, and the other current limit settings, etc. Then if we look a little bit lower here, so this is where the control mode can be selected. So in this case, in this demonstration, this is now already parameterized into this microgrid mode, or the mode 2 in this view. And all the settings that can be found in the real drive are available also here. And the idea here is that the scope of this tool is to have the possibility to simulate these events that are related to the grid connected operation, like power generating applications, and when you need to fulfill some grid codes. So you can find all the grid code parameters that are available in the grid converter application. So they are here under this parameter group. And the other consideration is that if you work in the microgrid or the grid forming mode, you can switch the mode here and run it as a microgrid inverter too. So also this standard AFE and the island operation are supported. So the mode can be changed like it is done in the real inverter. And it is possible to declare some of these parameters so that they are seen here as an external inputs. So basically now this base current reference, which is used to give or change the active current of the inverter, it is now declared as an external output, and it is seen so that if I go into this parameter group here, so I have selected this checkbox here, so it disables this parameter field, and it introduces this additional port here in the into the component. So then I can use these Simulink signal components to give some external reference here. So that is a short crash introduction to what is inside this model here. So I can now, before launching the simulation, I can briefly show the idea on the library browser side. So basically, the libraries that are needed is this Simulink basic library here, and you can actually use any of these components here now in this simulation. So these are mainly useful if you want to do some your own custom logic or monitoring purposes, or to calculate something, and for example, in order to give your own reference to the inverter, you could use components from this sources library here. So for example, I'm now giving this base current reference using this step block here. So in the beginning it is at value 0, and at time 1 second it makes a step change to final value of 80. So this is now from reference 0% to 80%. So that's the step change here. And what is more, the other toolbox needed is this Simscape here. And if I look into this electrical library here, so it offers now different types of components to build your own system model. So let's first look here. So for example, if you wanted to add some generic loads based on RLC components like passive loads, you can find this from the libraries. Then there are different motor models that you could use here. So as an example, you could set up induction motor model. So you had this grid converter case which involved the starting of these direct online motors. So basically you could investigate the startup transients by setting up a simulation which uses this kind of induction motor model here on the system side, and then use it together with this inverter model. And it also includes different types of other components like circuit breakers, which you can use in the simulation. And basically you can build quite a lot around these components. And in principle, it's also possible to use also these specialized power system components. So this is what was before this Simscape. So it was previously this Sim power systems, and now this is like an extra library inside this Simscape electrical. So these are traditional Sim power systems components, and these can be also used in the simulation if you use some specific interfacing components that are introduced here. So by using this one, you can also use these Sim power systems components. So that is shortly an overview on the libraries. So then when you set up a simulation in this Simscape, what is always needed is at least one electrical reference in the simulation, and this is the solver configuration block. So if you start from the scratch, this is something that has to be included every time in the simulation. Otherwise, it won't. It gives errors in the beginning. So these are like necessary components when you make these kind of simulation systems. From here, you can find just a short glimpse here. So the solver settings can be found here. So I'm now running a fixed step solver with a 10 microsecond time step, and this can be configured here. So next I will launch the simulation, and I will show what can be seen through these scope monitors here. So there was this one here. It was added into this demonstration model to investigate currents and voltages on the system model, and there is also another monitor view inside this component. We also show it, and it shows you some signals that are taken from the inverter model. So we can see also what the inverter is seeing here. But first, I double click to open this scope window here, and the simulation is actually already running there. So I will temporarily stop it here or pause. So if you look at the beginning, so the timing here is so that just briefly explain. So what is measured here is now the voltage here on the transformer secondary side. So this is the voltage that is supplied to the inverter, and here at this time point this breaker here is closed, and it also requires that this one is closed. So these two breakers are now closed, and the voltage actually, yeah, sorry about this one. So once this one is closed, we can see the voltage at the secondary side of the transformer. So that's this one here, and this is the grid current here, which is taken from this measurement component. And this one here, the third picture, this is the current on the primary side of the transformer, but it's the current then coming from the inverter. So we can see here that this is the instant where the inverter starts, or the breaker is closed, so that the filter is this is the filter in rush current, and this is now the current taken by the filter capacitors of the LCL filter. And actually this is the instant where the inverter goes online and starts here. And continue the simulation. So the idea here is now that there will be a load change. So this breaker here is closed, and we can see it closing at time 1 second, like this. So this is now the load current here flowing to this load here, and we can here now investigate the currents on the grid side and what is supplied by the inverter here. So idea is now that there is this load change occurring, and we are transferring this load from the network to the grid converter. So we can see that the grid current is now decreasing here because the inverter is increasing its output power supply to power the load. So the inverter is increasing its active output current with a ramp like this. So now it has taken over the load from the supply network, and although the network voltage is here available, this is now this demonstration is showing how to transfer this load from the supply network to the energy storage here. And what could be done during the simulation? So maybe it's not the idea of this simulation, but we can, if I pause it here for a moment, I can change the parameters here on the inverter model, so I can keep the simulation running or pause it for a while and then go here and make some adjustments on the parameters or change the reference here, or I could also change the reference values if I open these source components and modify something here. That will be also done. So basically this was a demonstration on how to install the toolbox, and then what can be parameterized here in the inverter model and what can be found in the libraries. And then I try to explain that the idea that you can use all the components that you have available in the toolboxes around this inverter model. So the purpose is not that we provide all the components for the simulation, but the main focus is now in the toolbox on this inverter model, and you can use any other toolboxes to build the system around it. And we also already looked at the scope window from the external measurements, but this is now showing some selected parameters or the signals that are taken from the inverter. So there is, for example, in this upper left-hand corner, so it is showing the active and reactive currents of the inverter. So the active current is increased with the ramp here until the reference that I showed you in the in this signal. It was changed at 1 second from 0 to 80%. So this is the base current reference, which actually means that it now in this simulation changes the active current of the inverter. So we can see that it starts here from 0 and the final value is here around 80%. And the reactive current, that is changing here due to the load. So the inverter provides a reactive current to keep the line voltage at the specified rated system voltage. So it supports the line voltage since the load is causing a voltage drop in the power system due to the load current, and this is now supporting the voltage by providing some reactive current. DC bus voltage measurement is here, and the phase currents are here, so we can use zooming tools to look at the currents here. So 3-phase currents, and it shows also the line voltage here. So it was a 450 volt network, and these are the RMS values of the line-to-line voltages, and this is the line frequency, 60 Hz. Here on the down left corner, this shows the status of the fault and alarm signals. So you can see that the values are here. Those are equal to 0, but if there's non-zero values, you can then refer to the application manual. So what is shown here is the codes are similar to what is used in the real inverter. So this was what I intended to show in the first place. So